Hello, my name is Rahul and I'll be presenting edge detection. What constitutes an edge? In a typical image, an edge will represent areas of significant change in the intensity of the image. It's mostly prevalent near the boundaries between two different regions of the image. Edges are commonly caused by surface normal discontinuity, depth discontinuity, surface color discontinuity, and illumination discontinuity. There are four main types of edges. Step edge, intensity abruptly changes. Ramp edge, intensity gradually changes. Ridge edge, intensity abruptly changes but quickly returns to the original level. Roof edge, similar to ridge edge, but the intensity changes are much more gradual. Purpose of edge detection. Identify points in the digital image where the intensity changes are extensive. Extract important features from the image such as lines, corners, curves, and textual data. Two of the most common methods for detecting the edge. First order derivative. The maximum value of the edge is located where the slope is the greatest. Second order derivative. The zero crossing of the second order derivative would determine the maximum value over the edge. Gradient. Gradient can be defined in the following function shown to your right. This can be approximated by a simple convolution mask. Roberts operator, created by Lawrence Roberts in 1964. It's simple to use because it can be implemented by a 2x2 convolution mask. Sobel operator, similar to Roberts operator, but it produces a much thicker edge and is less susceptible to noise. Can be implemented by a simple 3x3 convolution mask. Privet operator, works in a similar manner as Sobel, but uses a rather slightly different convolution mask. Find the maximum by using the zeros of second order derivative. Common second order derivative edge operators are Laplacian, Mayer-Hildreth, and difference of Laplacian. Laplacian, common second order derivative edge detection process. It can be implemented in a 3x3 convolution mask. Mayer-Hildreth, also known as Laplacian of Gaussian, or LOG. It's much more complicated in nature when compared to a typical Laplacian operator. Implementation. Gaussian filter to smooth the image, Laplacian operator to enhance the edges, linear interpolation to determine the subpixel location. By altering sigma value, it's possible to broaden the Gaussian filter. Note a large sigma value could make finding the edges much more difficult. Difference of Gaussian. It's an approximation of the Laplace of Gaussian, created because LOG requires extensive computational resources. It works by taking the difference between two LOGs. By picking two different sigma values, it's possible to adjust the width and obtain a close approximation to the LOG. Quality control. Most products created in a factory goes through some form of quality control. This assures the consumers that they're receiving a stable and consistent product. In this case, we'll use an image of a Coke can to perform the numerous checks for consistency. This can be achieved by using different edge detection methods. As you can see here, I've used three different filters. Sobel and Privet operator clearly shows the textual data. Second order derivative operators are useful in showing the outer edges much more clearly than the inner textual data. By simply adding noise, the first order derivative operators are greatly affected. Fortunately, the second order operator shows much more detail. Conclusion. If the original image is noisy, then it's best to use the second order operator. If the image is noise-free, then Sobel and Privet operator would work just as fine.